Okay, so we are go over the reaction kinetics today because the reaction kinetics is very important. We want to know the how fast the reaction is in our body. So um, uh, if we have a outside response, and then if we cannot respond the outside signal, our body may be in danger. So the reaction speed in our body is very important. So in most of the enzyme reaction in our body actually need the substrate, the enzyme. So substrate, and enzyme, right? So those substrate enzyme actually reversibly bind and dissociate. So make a substrate enzyme complex. So substrate, so there is an enzyme here, and then substrate will bind to the enzyme. So with the reaction constant, K forward, something like that. And then it also can dissociate. So going back, so it's with the reaction kinetics, reaction constant Kr, right? So when enzyme substrate bind to the enzyme, actually it makes a enzyme substrate complex. Then it can go to the, it can make the product as enzyme. This product can dissociate. So it makes a product here and then dissociate immediately because the enzyme have a specificity. So enzyme only accept bind the substrate, but nothing else. So substrate and product have a different structure. So it's very hard to bind the product into the enzyme again. So this is not the reversible reaction. It's only going to the product and enzyme direction, this direction, right? So we actually name the reaction constant K cat over here. So I'll tell you the why K cat is important later. Okay, so this is the model, very basic model of the biochemical enzymatic reaction, right? So this model actually can be made as a equation. So we want to know the speed of the reaction. Speed of the reaction is the delta product concentration over dt. So how fast it makes a product. So it can be with Vmax. So substrate over concentration over Km plus S, substrate concentration. This is Michaelis Menten equation. So I actually upload another video how to derive this equation from this model. So you can actually go over the video if you want to know how to drive this equation. So in this lecture, actually, I'll tell you what is the meaning of this equation. Right? So so let's go over the equation here. So if we have a lot of substrate concentration here, that may be much bigger than the Km. right? The Km is the nothing in here actually, right? So we can actually write down this equation V equal Vmax. So Km is does not affect anything, so it can be S substrate and then S substrate. So you can remove. So it's Vx. So if you have a lot of substrate, much more than the enzyme actually, so you can get the Vmax constant. So so in this reaction, right? If you look at the model, if you have a lot of substrate, actually this reaction, this is a reversible reaction. So mostly going equilibrium actually going to this way, right? Like a Le Chatelier principle. If you have a lot of substrate, they want to remove the substrate here. So most this equilibrium actually going to this way, and you have a lot of substrate and enzyme complex here. So the rate determining step in this reaction, this whole reaction is this reaction. So enzyme substrate to the making product. So the K cat is the rate determining rate constant. So so we can actually denote this one Vmax equal the K cat SE, something like that, right? So this is also K cat enzyme concentration, initial enzyme concentration, because the S concentration is much bigger than E0, the initial enzyme concentration. So SE equal E0, because all the enzyme actually bind with the substrate. So you can get the Vmax, the maximum speed of this reaction, and then also kcat number if you have saturated concentration of the substrate. So experimentally, how can we get the Km and kcat number? So we need to measure the rate constant and draw the graph like reaction rate. And substrate concentration. And then we can draw those kind of a graph by experimentally. And then we using the linear regression, you can actually get the Vmax. This is maximum speed of the reaction. And then also you can calculate the half Vmax. So the point, the concentration of the Vmax, half Vmax, it will be a Km here. So you can get the Km number by experiment using this graph, and then you also get the Vmax number by the experiment, and also you can get the kcat number because you know the Vmax and E0 concentration here. So what is this is meaning? So this Vmax is the high substrate concentration the maximum enzymatic reaction speed. It can represent the maximum enzymatic reaction speed. And then Kcat is the turnover number. So this enzyme needs to be recycled after make a production. So Kcat actually include the how fast this enzyme can be recycled here. So it can make a substrate enzyme complex again, and then make a product, and then going back to here, so and then make it again. So if the enzyme recycling efficiency is very low, Kcat probably are very low. So the reaction speed will be very slow. But the recycling efficiency is very good. So the reaction speed will be fast comparatively. But this is just a model, Bayesian model. So we in the real life actually there are many enzymes, reversible enzymes. So product can bind to the enzyme and then make a substrate, something like that. So PE and then make a substrate again. So this kind of enzymatic reaction, this equation cannot be applied. So we need a more complex equation. And also, if we have stepped the substrate binding, like the substrate 1 plus enzyme, and then it makes a substrate 2 plus substrate 1E enzyme complex, and make a substrate 2, substrate 1 enzyme complex, and make a P plus E, something like that. If some enzyme reaction has the ordered substrate binding, that also cannot apply with this reaction. So we need to do research, a lot of research, how your enzyme work actually in the biochemical reactions. You need to set up the model, new model, and then you can calculate the another Bmax and Kcat constant, and you can actually evaluate the enzyme efficiency of the reaction. Okay, and then also the very old days actually when the non-linear regression is very difficult at the time, because right now it's very easy because we have a computer, but at the very old days, it was a little bit difficult to get the nonlinear regression curve. So we sometime before use the double reciprocal plot, like the reaction rate, 1/reaction rate versus 1/concentration, substrate concentration graph. So you can actually make this graph, graph looks like a linear here. So it is much easy to make the linear graph. I mean, get the linear regression graph. But in this case, it has a lot of error. Error rate is much bigger than this nonlinear regression. So nowadays, this is not very much used. Most people actually use this graph, and then with the linear regression curve. So yeah, so that's it. Okay, thank you.